thanks very much for the invitation. Uh, 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 Let me start with the motivation. Actually, I'm cheating a little bit. My motivation was slightly different, and I will tell about that later. But the obvious motivation is classical Schottky problem. So let me restate this problem in the following way. How to find out that a given principally polarized g-dimensional complex abelian variety, so stands for an abelian variety, lambda stands for principal polarization, is not isomorphic to the canonically polarized Jacobian of a smooth projective irreducible curve C of genus G that is greater than 1. Then again, this fancy J stands for the Jacobian and theta stands for principal polarization. Well, so let me remind you that if fancy MG be the coarse modular space of such curves, then its dimension is 3G minus 3, which is positive because G is strictly greater than 1. And if you consider the coarse modular space of all principally polarized abelian varieties of dimension G, with this fancy AG, then its dimension G times G plus 1 over 2. So, well, now the Torelli theorem says that the map from MG to AG, which assigns to each curve C is Jacobian with canonical polarization theta, is injective. So this pair determines the curve C uniquely. And the Schottky problem may be stated as follows: how to describe the image of this map? Well, we study principally polarized abelian varieties X lambda with additional symmetries. Namely, we deal with the, so again, I'm not going to offer another solution of great Schottky problem. My task is rather modest. First, I consider a pair of X lambda that admits an automorphism delta of prime order P, where P is strictly greater than 2, because for 2 is not interesting, whose set of fixed points X delta is finite. It turns out that certain natural conditions on the multiplicities of eigenvalues of the action of delta on omega 1 x, which is differentials of the first kind, do guarantee that those polarized varieties are not canonically polarized Jacobians of curves. So here's the main idea. A group action on the polarized Jacobian is almost induced by a group action on the curve. It's an trivial variant of Torelli's theorem. And main technical tool, a golomorphic Lefschetz fixed formula for curves that is due to Atian bot. It's a very special case. Now let me introduce notations and assumptions. So as usual, C is the field of complex numbers, P an odd prime, mu P the multiplicative group of P's root of unity, zeta P is just, we fix a primitive P's root of unity, exponent of 2i pi over P, and many things will have kind of main character will be a group G, the group of unit of the field of residues modulo P, of the ring of residues modulo P. Well, so just a notational remark. If H an element of G, then we denote by negative H the product of H and negative 1 modulo P. Well, X an abelian variety. We write G for its dimension. That is always positive. Well, if small z is a point on X, so everything will be over complex numbers. So when I'm talking about points, it would be just complex points. Then capital T subscript Z from X to X is just the translation by Z. It maps X goes to X plus Z. Omega 1x, the G-dimensional space of holomorphic one forms of an X. Well, let's consider an ample divisor D on X. Now, this divisor gives rise to an isogeny from abelian variety X to its dual, which may be considered as peak 0 of X. Well, probably zero should be superscript but not subscript. Let me denote it by lambda d. That maps as follows. If you take a point small x on our capital X, we will take inverse image of our divisor d under the translation, subtract d, and take its linear equivalence class. So this map is an isogeny of abelian varieties that depends only on the algebraic equivalence class small d of our divisor d. Well, and these are classes, though. They lie in the neuron severity group of X, neuron severity of X. Well, if our small lambda, which is our capital lambda d, is an isomorphism, then it is called the principal polarization defined by d. There is a kind of easy criterion that tells us when our divisor d defines the principal polarization. Well, it should be ample. Actually, to be effective is good enough, and its self-intersection index should be g factorial. So so these conditions are equivalent. Now let me remind classical result about Jacobians. So let's take our curve C, which is a smooth projective curve of genus G greater than 1, with Jacobian J of C. Choose a based point P on C. And then to such a point corresponds the regular embedding of our curve C to the Jacobian. Namely, each point Q on our curve C goes to the linear equivalence class of degree zero divisor, which is just difference of points Q and P. Well, our G of C is an algebraic group. So using the group law on G of C, we may extend this map that is denoted by alp P, where alp is short for Albanese. One may extend alp P to the regular map of the G1's minus 1's symmetric power of C. Namely, to each point of this symmetric power, well, we may associate a collection of g minus 1 points on C, Q1, etc., Qg minus 1. Let's take the image of each of those points and take the sum in our Jacobian. Well, and the image of this symmetric power, g minus 1 symmetric power, which is denoted by small theta p, is an ample divisor on G of C. Well, if you take the G symmetric power instead of G minus 1, you get a birational map, but I don't need it. Well, actually the class, the algebraic equivalence class of this theta p does not depend on the choice of p. Actually, if you change p, you get just the translation of this divisor. Well, the principal divisor, the capital theta, which is lambda theta of G of C, is called the canonical principal polarization of the Jacobian. So again, as I already pointed out, we will deal with pairs, with abelian varieties x lambda with additional symmetries. So x lambda admits an automorphism delta of prime order that p is just strictly greater than 2, whose set of fixed point x delta is finite. Well, sorry, it seems that something is okay. So now let's forget for a while about curves and look at triples x lambda delta, where x is an abelian variety, lambda principal polarization, delta is an automorphism such that delta satisfies the Peace cyclotomic equation. Again, p is not prime. So Peace cyclotomic equation, delta to p minus 1 plus delta to p minus 2 plus delta plus 1, which is just sum of powers of delta from k0 to p minus 1, is 0 as the endomorphism of x. Well, this condition is equivalent to the fact that P's power of delta is the identity map, and the set of fixed point of delta is finite. So this condition and these two conditions are equivalent. Well, now we have a polarization lambda. I want lambda to be delta invariant. Well, this means that if lambda corresponds to divisor D, then the algebraic equivalence class of D coincides with the algebraic equivalence class of the inverse image of D under delta. Equivalently, this means that delta star delta equals 1, where U goes to U star is the Rosati involution on the endomorphism of a ring of X with respect to lambda. Well, generally, Rosati involution is defined not on the endomorphism ring of X, but on the endomorphism algebra of X. But since lambda is principal, it actually acts on the endomorphism ring. Now, the linear operator delta omega from omega 1x to omega 1x induced by delta has the collection of G eigenvalues. Let me denote this collection by capital A, so it's alpha 1, alpha 2, alpha G. And all of those guys are primitive piece roots of unity. Well, these conditions means that 1 is not an eigenvalue. So each alpha k is of the form is zeta p raised to some power nk, where nk is an integer that sits between 1 and p minus 1. Well, again, as I pointed out already, x delta finite means that 1 is not an eigenvalue of delta omega. Please ignore this star. Well, and here's our main tool, multiplicity function. Ax delta from G, our group G, which is z pi p z star to z plus. Maybe I should warn you that for this talk, z plus is the set of all non-negative integers, so 0 is included. And this function is defined as follows. Ax delta for n mod p, which is, if you like, the multiplicity, is the number of integer is just the number of eigenvalues such that that coincide with nth power of our zeta pn. So we have linear operator. It has eigenvalues. And this is just multiplicity function that counts the number, that counts the multiplicity of each eigenvalue. Well, and maybe I should point out that this operator is semi-simple, so there are no Jordan blocks, just because it's periodic. Well, now some technical definitions. For a given G and odd prime P, we call a function both A from G to Z plus well-rounded if sum of values of A at H and negative H is to G divided by P minus 1 for each A and J. Well, which certainly implies that the sum of all the values of our function A is G, if we do summation across H. Admissible if there is a triple x lambda delta such that our function A is a multiplicity function that corresponds to pair x delta, where x is abelian variety, lambda principal polarization, and delta periodic automorphism that satisfies the properties mentioned earlier. C admissible if there is a I am just repeating these conditions, x lambda delta, etc., but x lambda is actually the Jacobian with canonical polarization for smooth connected projective curve C. So we are looking for three classes of function: well-rounded, admissible, and C-admissible. All are non-negative integers values functions on our group G. Now let me list some facts. Certainly C-admissible function are admissible. Second, that is that every admissible function is actually well-rounded. It requires some efforts to check it, but it's known. Third, Well, third condition is kind of trivial, that the number of well-rounded functions for given J and P is P, is the power of sum of 2G over P minus 1 plus 1 raised to power raised to P minus 1 over 2. It's just straightforward. And fourth property, an admissible function exists if and only if P minus 1 divides 2G. I believe this fact somehow goes back to Shimura and Ken Ribbit. So there are three classes of functions, and we are mostly and we are interested in finding out which which well-rounded functions are C-admissible. In this talk, we discuss an explicit formula for kind of explicit formula for C-admissible function Ax delta for given G and P, geography in G-plane, for which pair GP there exist C-admissible functions, admissible functions that are not C-admissible, with special references to the case P equals 3. Well, applications of the method. Actually, this application was the main reason why I started to do it some time ago. A relatively cheap proof that certain canonically polarized intermediate Jacobians and prime varieties are not isomorphic to Jacobians of curves. Now, well, let me give an example of C-admissible function. Fix prime P, choose an integer m that is strictly greater than 1, that is not divisible by P, and put G half of the product m minus 1 P minus 1, which looks like the formula for the genus of a curve. Take a polynomial f of x with complex coefficients of degree m without repeated roots, and consider the affine curve C tilde of P defined by equations y to P equals f of x. It's a plain affine smooth irreducible curve. Let's look for by its smooth projective module CFP with Jacobian J, fancy J, defined automorphism delta tilde of CFP by, well, we have a formula for C tilde of P, so x and y are rational functions on this curve, and the formula is just xy, x remains unchanged, while y is multiplied by our primitive piece root of unity. By functoriality, delta tilde induces the automorphism delta of j theta, which satisfies the piece cyclotomic equations. Well, this result for p equals 2, I believe, was known for h, for arbitrary p and for arbitrary polynomials, not necessarily without repeated roots, etc. I believe it was it has appeared in papers of Björn Punin and Ed Schiffer, maybe in another paper of Schiffer, maybe in paper of Stoll. Well, again, it is quite well known. So now, well. So we have this automorphism and how its multiplicity function looks like. It looks as follows. Let's look for its value at elements of our group G. That is, let's evaluate it at point minus k modulo p, where k is an integer that lies between 1 and p minus 1. Well, it turns out that we have to do the following. We have to multiply k by m, divide by p, and take the integer part. So it's an example of an admissible function. Well, let's check that it's correct. Well, actually, it's well known that there is a canonical isomorphism between differentials of the first kind on the Jacobian and on the curve, induced by our embedding. Well, now our and this isomorphism is equivariant with respect to our periodic automorphism. Now we may write down explicitly eigenvalues on the differentials of the first kind on our curve. Namely, it's the differentials of the form x to I dx divided by y to k, where k varies between 1 and p minus 1. and I varies between 0 and exactly this guy minus 1. And there are precisely G such pairs I and K. Well, and again, if you look how our automorphism delta acts on those differentials, then this guy is multiplied by zeta p raised to power minus k, because x is not changed and y multiplied by zeta p, so we just divided by zeta p to k. And so we get that the multiplicity is exactly this guy without this one, because 0 is included. Now let me state the main result. Necessary and sufficient conditions for functions to be C-admissible. Fix P and G such that P minus 1 divides twice G. Recall that our G is just Z by PZ star. And now, well, I need to recall some basic things from Fourier analysis for finite groups, finite cyclic groups, I would say. So the convolution of functions f1h and f2h on G is the function f1 star f2 of h is the following. You have to do summation across G. You have to multiply value of 1 at U by the value of 2 at U inverse H, sum them across U and divide by P minus 1, because P minus 1 is the cardinality of G. And I need this function, bold J, from G to 1 to P minus 1, which is just rather straightforward things. If element H of G is K mod P, where K sits between 1 and P minus 1, then G of H is just K. So it's just the lifting, so to say, of elements of G to Z. Okay, now it's time for main result. A well-rounded function. Let me remind you that a well-rounded function is the function that that satisfies this condition. A of h plus a of minus h is to G divided by P minus 1 for all h. So a well-rounded function a to G to Z plus is C-admissible if and only if there exists a function b, integer, non-negative integer valued function, such that the following condition follows. The sum of values of this function across the whole G is this ratio to G divided by P minus 1 plus 2. Second, if we take a convolution, a kind of convolution of B and J and not divided by P minus 1, then the result will be divisible by P. So we take a product of B of H by our J at H minus at inverse of H and do summation and get some integer, obviously some non-negative integer, actually, and it should be divisible by P. And the last condition, certainly the most important, it tells you how you could obtain A from B. Namely, what we need to do, we need to take the convolution B and J, evaluate it at point negative h, and multiply by P minus 1 divided by P. So what we do, we just do summation of the products of B of A and J of minus inverse of U times H, divide by P, and subtract 1. And this gives you the formula for function A. So these are necessary and sufficient conditions for our function A to be C-admissible. Now let me sketch an ideal proof. So only if y starting with a C-admissible function A, we could get such a B. Assume that our principally polarized x lambda comes from the Jacobian, G of C theta. Torelli theorem says that any isomorphism of polarized Jacobian is always induced by an isomorphism up to sign and translation of curves. So delta is induced by some delta tilde, which is automorphism of our curve C. So we have a commutative, such that we have a commutative diagram. C goes to G of C. It's just Albanese. It's just the embedding we discussed before. Here we have well, I supposed to have here delta, but actually I'm writing phi of delta because phi of delta may differ from delta by translation. And here, and here, and here, and here, and here I have some automorphism delta tilde of C. And again, phi of delta is almost delta, but anyway, we have this commutative diagram, which implies another commutative diagram. Here we have on this line we have a canonical isomorphism between differentials of the first kind on the Jacobian and the curve here and there. Here we have automorphism induced by delta tilde, but here we have delta omega. Why not? Why not phi of delta omega? Because all the forms on the Jacobian are invariant under translation. So from the point of view of the action on the differential of the first kind, is the same as our delta. Okay, so we have this commutative diagram. Now, let gamma be the subgroup of in the automorphism group of C generated by our delta tilde. Well, we know that one is not an eigenvalue of delta tilde omega because it's not an eigenvalue of our delta omega. This implies that there is no invariant delta tilde invariant form on C. Therefore, if you consider the quotient of C by gamma, we get the projective line. If we get a curve of higher genus, then it would have a non-zero holomorphic form, and we could lift it to C and get a gamma invariant form. Well, now, by Hurwitz's formula, well, certainly the degree gamma has order p because everything here has all the automorphism here will have period p. So we may apply Hurwitz's formula. It tells us that delta tilde has exactly 2g divided by p minus 1 plus 2 fixed points. And let fix be the set of fixed points of this delta tilde. Let our q be a fixed point. Then delta tilde acts on the one-dimensional tangent space to C at q as multiplication by some root of unity, by epsilon q, which is actually zeta p, our zeta p raised to power nq. And this guy is denoted by the index of q. Well, one may check that every q is non-degenerate. In other words, each index is not 1. Well, now let's look. So we have linear maps. We are interested in eigenvalues and their multiplicities. So it's time to do the trace. So the trace of the map induced on the differentials of the first kind on X by definition, well, what we denoted by tau is the sum across all elements H and G, Ax delta of H and zeta p of H. Because again, Ax delta of H is exactly the multiplicity of zeta p of H as an eigenvalue of this operator. Well, tau coincides with the trace of delta tilde omega in omega c on the differentials of the first kind on our curve. Now, Let's apply holomorphic Lefschetz at fixed point formula that tells us um, that 1 minus tau bar is actually a sum across the set of fixed points where we should look where we should consider inverse of 1 minus index of the corresponding point. Well, and then this guy is a sum again across our group G of B of H divided 1 minus zeta P of H to raise to power H, where B of H is the number of fixed points with fixed index. Now what we need to do, just compare two sides of the equations. On the left hand side we have this sum, on the right hand side we have this. And please take into account that those zeta p raised to power h is the basis of the q vector on the p cyclotomic space field which we consider as a vector space over q. So basically, we just need to develop to present this this inverse as a linear combination of zeta p of h. That's how we get the convolution stuff. Well, proof in the opposite direction. Assume that a function b meets our conditions. So the sum of values is 2g over p minus 1 plus 2. And the sum of b of u times g of u inverse across the sum it is taken across elements of G is divisible by P. We construct a smooth connected projective curve C of genus G. Well, let me do the case G is at least 2. The case G is 1 is really easy. Such that the Px lambda is endowed with an automorphism delta of period P with finite x delta. And our x delta is obtained from our function P. In particular, well, what we get, if that the value of our function x delta at minus 1 mod P will be exactly 1 over P of this expression, minus 1. So this since we'll see that our x delta takes on integer values, this would give us the integrality condition, if you like. Anyway, to construct such a C, we choose p minus 1 polynomials fh, non-zero polynomials. They're indexed by elements of our group G, such that its degree of fh is b of h. Fh has no repeated roots. They're relatively prime for distinct elements of group G. Well, and in particular, fh is non-zero constant if and only if b of h is 0. Now, well, let's take as polynomial f of x, the product of polynomials fh raised to power of g of h inverse. Remember, we introduced a certain function j on our group G. And consider the affine curve C tilde defined by the equation y to p equals this f of x. C is smooth projective module, and we have an obvious automorphism of period P. Xy goes to x zeta py, and take the Jacobian with induced delta. Well, DF computation shows that x coordinates of fixed points of delta tilde are precisely roots of f. If alpha in C is root of h, then there is precisely 1p in C with x coordinate alpha. In addition, the index alpha p is zeta p of h. Now, homomorphic Lefschetz fixed point formula implies that our A is obtained from B in the way we wanted. Now, here is a natural question. We say that function b defines a. Does a define b? So, theorem, let b prime be another complex valued function on G. On, the following two conditions are equivalent. First, our function b prime also defines we may obtain our function a from b prime using the same formula with convolution. Second, the odd parts of function b and b prime coincide. In other words, b prime of h minus b prime of minus h is the same as b of h minus b of minus h. And the sum of values of b prime is the same as the sum of values of b, namely to g of p minus 1 plus 2. Well, and this assertion follows from the non-vanishing of Fourier coefficients of function j for all odd characters chi of our group G, which in turn follows from the non-vanishing of the value L function at 1. Okay, now let me consider a special case when p equals 3. Then we could give an explicit description of all C-admissible function. So in this case, we may identify the group G with a pair of elements 1 bar and 2 bar, 1 mod 3 and 2 mod 3. So let A be a function on G, non-integer, non-negative, such that A of an A1 bar plus A of 2 bar is G. In other words, A is well-rounded. Then first, A is admissible. It's easy to check. And the number, which means that number of admissible function is G plus 1. Second, A is C admissible if and only if these values sits between G minus 1 over 3 and 2G plus 1 over 3. A priori, we know that they may sit between 0 and G. And here's the restriction for C admissibility. Now let's find the number of C-admissible function A3 of G for each G. Well, the answer depends on behavior of G modulo 3. If G is 3k plus 1, then A3 of 3k plus 1 is k plus 2. It just follows from this. If G is 3k plus 2, then A3 of 3k plus 2 is k plus 1. And if G is divisible by 3, it's 3k, then A3 of 3k is k plus 1. Please compare this number with this G plus 1. In all cases, there are at least 2G minus 1 over 3 admissible but not C-admissible functions. So yes, indeed, there are admissible functions that are not C-admissible. So they occur as multiplicity functions for abelian varieties, but not corresponds to jacobians. Example corollary. If p equals 3, g equals 5, then each C-admissible functions, there are just two of them, does not take on values 0 or 1. Corollary. Assume that pair x lambda, where dimension of x5 is endowed with an automorphism delta such that delta square plus delta plus 1 is 0, just cyclotomic equation for p equals 3, if either a of 1 bar is 1 or a of 2, 0 is 1. Excuse me. Then x lambda is not isomorphic to the Jacobian for a smooth irreducible projective curve. Applications. And actually, this application was the main motivation for me to do this. For a smooth complex projective threefold T, Clements and Griffiths introduced the intermediate Jacobian, which is a principally polarized abelian variety, and proved that this guy is not isomorphic to Jacobian or a product of Jacobians. And they used it to prove that a smooth cubic T is not rational. It was one of famous counterexamples to Lur's problem in dimension 3. we will do part of second assertion in a relatively easy way for a smooth projective cubic threefold defined by the equation y cube equals f of x0, x1, x2, x3 in P4, where f is an irreducible homogeneous cubic polynomial. There is an obvious automorphism delta tilde of t defined by, all x coordinates remain of change, but we multiply y by zeta 3 by primitive cube roots of unity, which induce a periodic automorphism delta of g of t of order 3, which satisfies this equation, delta squared plus delta plus 1 equals 0. For the corresponding intermediate Jacobian, using results explicit computations of Griffiths and Toledo, we get that the multiplicity of the corresponding multiplicity of a of n bar is 4, and multiplicity of at 2 bar is 1, which proves that this intermediate Jacobian for this cubic is not the polarized Jacobian of a curve. Unfortunately, it's not good. It's still not. In order to prove that this guy is not a rational variety, one has to do a little more, namely to check that this guy is not isomorphic to a product of polarized Jacobian. That's what I can do, but still still I can prove that it's not the Jacobian, and that was a motivation for all this stuff. Now, well, in general case, for p equals at least for arbitrary p, our convolution formula tells us explicitly when our function is not C-admissible. So, namely, assume that our function a on G is C-admissible, then all its values sits between 1 over p of 2g minus 1 minus p minus 2 over p from below, and from above, we should subtract from 2g p minus 1 the same expression. Well, so here this formula, and now an application, because all the time we were talking about principally polarized abelian varieties that are not polarized Jacobian. So of course, it would be tempting to figure out whether these varieties are not Jacobians if we just ignore the polarization. So let me state the following assertion. Consider a triple x lambda delta, which is delta, let me denote it by delta x as above, where prime p is the order of delta. Well, and it satisfies the square-atom equation. Let g equals dimension of x and r be positive integers, such that r times 2g divided by p minus 1 is at least p minus 1. Suppose that actually endomorphism ring of x is actually generated by our delta. So endomorphism X is actually the p-cyclotomic ring. And suppose that sum of the roots, primitive p roots of unity, is not an eigenvalue of our automorphism delta acting on the differentials of the first kind. So a of x delta x of h is 0 for some h. Then the r-dimensional abelian variety y, which is r's power of x, is not isomorphic as an algebraic variety to the Jacobian of a smooth connected projective curve of genus GR. It just follows from the main inequality that appeared on the previous slide. Because, well, if this guy is positive, this means that that means that a of h should be also positive for all h. But if you increase g, and multiply it by some constant, then this term would become higher. However, if you consider if you take powers of our x, the multiplicities will be just multiplied by r. But if some multiplicity was zero, then you may multiply it by any number, and you still got zero. And so here's a sketch of the proof. We have the diagonal embedding, 0 zeta p, and it embeds to end of x, which sits at index r, which is our y. Well, and this guy, well, certainly it does not coincide with the whole endomorphism ring of y, but it still coincides with the center endomorphism of y. And this center is just the p-cyclotomic ring, which admits precisely one positive involution, namely the complex conjugation. So this means that our automorphism delta y respects any principle, actually respects any polarization of y. But so we may apply our previous results and get that the multiplicity is zero. But this contradicts main inequality, which ends the proof. Again, here it's important that the polarization actually, I believe it's useful observation. If you have an automorphism, a central automorphism of abelian variety, and if it respects one polarization, then it does respect every polarization. So, well, and here's an example, probably it will be to this. Let G is half of p minus 1, and X is simple abelian variety of primitive CM type with multiplication by the p-cyclotomic ring, Z of zeta p. So endomorphism of X is just Z of zeta p. Then we have multiplicities a of x h plus a of x minus h is 2g over p minus 1, which is p minus 1 by p minus 1 is 1 for h. And therefore, either ax of h is 0 or af of negative h is 0, well, which is well known. If you have an abelian variety of CM type, then its CM type includes only one element of any pair of two complex conjugates embeddings. Well, and this follows from the previous results that if R is at least p minus 1, then x to power R is not isomorphic to a Jacobian, even if you view it as an algebraic variety, just ignoring the polarizations. Well, and the example when G equals 1, P equals 3, and R equals 2 is well known. In particular, if E is an elliptic curve with endomorphism, whose endomorphism ring is Z of zeta 3, the third cyclotomic ring, then E square contains no smooth connected projective curve of genus 2. Actually, well, you may ask what about other elliptic curves with complex multiplication, say by the full ring of integers in the imaginary quadratic field. Then, well, the same is true for fields with discriminant. Well, here we have discriminant minus 3. Well, the same is true with discriminant is negative 7 or negative 15. For other discriminants, this guy is actually isomorphic to a Jacobian. Well, I guess I should stop here. Thank you.